welcome back to Engineers Workshop. Over here by the K&T rotary head mill. I'm going to be starting a new project today, and I'm going to say that this is probably my most challenging project to date, being not for duration or anything like that or horrible calculations, but just the complexity of the part that I'm working on, how to hold it. And make the long story short, it is the body of a Bosch injection pump for a Volkswagen TDI engine. And there's a port in the top of this that houses, it's really a pressure relief valve that sets the pressure of the primary vane pump in the body of the pump to like 125 psi. And the port in this aluminum casting got stripped out. The thread is a M14 or M16 by 1 millimeter, which is like an extra fine thread. There is a tap available for it, thankfully, but I have to bore it out and sleeve it is what I'm thinking I'm going to have to do. But let me show you the part and the complexities of holding this thing, and then we'll get started. Okay, so here we have it. It's basically stripped down to the bare casting. The drive pulley, which is a timing belt, is on this input shaft. And then basically the first part of this pump against that front face is a vane pump. And the vane pump draws in fuel and pressurizes this entire cavity by compressing the fuel against a spring that is in this device right here. So you can see that it seals both at the top of the bore and at the bottom, so it divides this bore up into a couple chambers. And if you look at the bottom of this, there's a spring, pretty stiff. And I can compress the spring, and by lifting that spring off the seat, that's what sets your pressure in the pump body. So let's get a little bit more light in here, zoom in on this, and then you can see what happened. Now, it's a little difficult to see, but the top portion of the hole, we've got a lead in, we've got a smooth bore, and we got what should be threads starting there. And you can see they've been pulled out down about 1/8 inch. Now down at the bottom, actually, I can reach down there and grab some of the threads that have migrated into the bottom of the hole. And it looks like there's another one in there. But basically, about 1 inch down, we have another taper that second O-ring on the bottom engages with and seals off the bottom of the hole from that middle part. And complicating things, if I can get here with the right angle there, you can see there are ports into the side, and even that one comes right on up into the threaded area. Basically, I'm just sticking the points of the forceps there, the tweezers, into that port. So the insert that I make, it has to basically stop flush with the top, because that's where that valve lands, and that positions, the relative positions of those two O-rings vertically in the bore. And it can't go down really much farther than where that side port starts. So we're looking at an insert that's probably no more than 1/2 inch long, and that has to have this thread on it. And it's a M14 by 1. So the plan is use the 12L14 leaded hex stock that I bought to reproduce fasteners on the economy engineering lift and use that to make the insert, bore it, get the correct tap diameter for that thread. I'll probably use the tap in the lathe to tap that hole. Then I'll start working the OD down to something that will be appropriate for inside this boss. Don't want to make it too thin, because even though we're pressing a steel insert into an aluminum body, steel's 3 times stronger than aluminum, but that insert will collapse with a press, and then it'll be too tight on the threads. So we're going to try to keep the body diameter bigger, maybe out past that witness line, or even a little bit towards the outer counterbore here. And then that way, when I do a light press, maybe 0.5 thousandths to 1 thousandths. I'll also use some like some bearing retaining compound, Loctite, to ensure I've got a seal. But put the insert on the little valve, and then that way, once this starts in that bore, that lower end can start piloting, keeping things straight as I tap this guy or press it into place. So that's the plan. And then this is going to be sent off to a specialty place that builds these manual injection pumps for the TDIs, and he's going to reassemble this thing with all the pieces and make sure that it's ready to go. That's the plan. Let's see how. First issue I have machining this is how to hold it. I did try clamping it in the vise end to end. It will fit, but there's not a lot of contact because of all the projections down here. Plus, I didn't want to be squeezing this thing and risk distorting it. So I think the safest way to hold it is to make a mount that essentially uses the 3 tapped holes and projects this through some plate. So I have a piece of 1/4 inch plate here in the vise, and this pilot diameter, which is probably metric, is 2.672, and I'm going to give it a few thousandths clearance, and then we'll put a hole in this plate that's 2.685. That'll give it about 7 thousandths clearance. And putting holes of any size, any diameter, is something that the K&T 2D excels at. So we'll show you how I'll set that up. I have a 1/4 inch 2-flute solid carbide end mill in the smaller collet. These are K&T collets. I did confirm the diameter is 0.25, so as long as it's cutting at that diameter, what I set on the dials here should be accurate to within about 1 thousandth of an inch. So we'll see how I do. We'll measure the actual hole once we're done. Let's go ahead and get this located, and I'll show you how I set the offset. So what we're trying to accomplish is locating hole with a diameter of 2.685, and we're going to be cutting this with a 1/4 inch milling cutter. The radius of this is 1.3425. So if we draw our 1/4 inch bit in here, that has a center, and what we need is the distance between this and the center of that cutter. That distance right there. So radius of this is 1/8 inch. So the distance from here to here is 1.3425 minus the 0.125. That leaves us with 1.2175 offset. So we will set up on 0, offset the spindle 1.2175, and then as we mill, that will give us a hole diameter of 2.685. So up here under the quill, we have our scale, which you can see is set at 0. There's a hash mark inside that little counterbore. We can go 1 inch in this direction and up to 4 inches in that direction. Each crank of the handle here is 100 thousandths. Actually, I have the slide locked, so I want to make sure that's unlocked. So to set our offset for this hole, we have a radius of 1.2175. Each crank I do here is 100 thousandths. So we're going to go till we get to the 1, 100, 200. And for the final amount of this, which we're going to be reading directly in thousandths, is the 175. So that's 1.2, 1, 5, 6, 7. And we'll split that reading there and get a half thousandths. So the secrets I've found to accurate holes on the K&T are 1, a rigid setup, 2, sharp cutters, and 3, locking that offset with these 2 lock nuts, one on each side, so that this can't creep in or out during the cut. And since we're going to be plunge cutting this and not creeping up on a specific diameter, I'm going to go ahead and lock these. I have, you can make cuts with those locks not engaged, and you can adjust the cut as you're going and take, another thousandths off here or there. But for this, we're gonna lock that down. Now, the next thing will be to set the limits of this hole. I want to come within about a ½ inch of this edge and within about an inch of this edge. And I'll show you how we do that. So now we have our offsets in place, and when I engage the head is going to rotate, and you can see that this is traveling in an orbit. So since I have, and we got, bidirectional control, and right now the spindle has actually offset towards the back. So with this on 0 degrees, I can move the table back and forth, and I'm going to bring the cutter down, and I'm going to crank out the y-axis until that cutter is just kind of grazing my Sharpie mark. There we have it. Now I'm going to go ahead and I'm going to put the offset at 90 degrees to the left, and I can also, crank that and make it go faster. Right now I have the orbital speed of the head set at the approximate inch per minute cut. FS Wizard says 2,500 RPM and about 8 inches per minute. So doing all the math, that comes out to 1/2 RPM. Okay, so that gives us a location of this circle, which is going to be about 1 inch from this edge and 1/2 inch from that edge. I can come over here to the DRO and I can zero that. That tells us where the center of the spindle is. So let's fire up, and we'll do the clearance hole in about 3 passes, 100 thousandths, 100 thousandths, and then the last 50 thousandths. I think we'll do a witness line just a few thousandths deep to make sure things are acting as they should. I think we're good. Let's go ahead and dial down 100 thousandths step to cut. I'm going to keep it at 50 just because it's sounding like it's not liking it too much. pass, I bring it down another 50 thousandths over about 1/4 of the revolution. Well, I changed out my tool because I don't know what's going on, but this one definitely seems like it's being overworked, and even the collet is kind of hot. I don't know, I've found in the past that the feeds and speeds suggested by FS Wizard are kind of optimistic. So this is a 3-flute titanium nitride coated solid carbide end mill. So let's finish up hopefully with this one sounding a little better. And I'm running 1600 RPM now. I'm running against my quill stop. I need to drop that down. Oh, I think I'm through. We'll let that do a spring pass around the perimeter and call it done. Feels pretty good. Let's see where we're at on the calipers. Don't know that you could ask for a better result. That was the target. Five thousandths fit. Now I will spot those holes and drill clearance holes through the plate. I found metric fasteners that fit this, and I just measured the diameter, and turns out this is an equilateral triangle, so that makes setting up the mounting holes pretty easy. And the circle diameter on this doesn't really correspond to anything nominal, metric, or English. It's 1.925. It's like just shy of 49 millimeters, but making circular, radial bolt patterns is one of the things that the K&T excels at. So let's just put these mounting holes in using the rotary head. To get the correct offset for these holes, I need to dial in some additional spindle offset to 1.925. So we're going to go ahead and rough crank this out to 1.9. So we're at 1.90, so 1.9, 1, 2, 5. First hole is what I would call in the 6 o'clock position. So once we get this oriented, we'll see on this scale what that is. I think that's 180. So that's 180. Thought I had a 3/8 stubby drill. I don't. So this is slightly larger than a 1/4 inch. Has a 1/4 inch step shank. I'll punch the 3 holes and I'll enlarge them, probably just on the drill press, and then that'll complete this plate for mounting up that pump body. I have my quill stop set so that once that punches through, it'll basically stop the downward feed. And the feed I have set, which is unfortunately on the back side here, is 1,000ths per revolution. I got about 1,000 RPM on the drill. So let's punch one of these holes and see how we do. We'll do one on the side here where the quill feed, so you can see that do its thing, and then I'll reorient you to as we do the other holes, so you can see what it does with the feed wheel. And now we index our head 120 degrees. Hopefully one of these boring heads, this one isn't much shorter than this one, will fit, and with the pump and everything in place, and I'll be able to drop the knee, and all of this will go under this spindle with room to spare. Okay, I don't want to get things too tight, because what I'm going to have to do is square this. If I had ever leveled my machine, which it is not, I could just level the top of this, but machine still really isn't in its permanent position, so I'll just put a parallel on here and indicator and sweep from one end to the other. But I think I've got enough room, because if I take a boring bar, I can put the boring bar in there, and I think I'm good to go. I do have some smaller ones, but unfortunately they have smaller shanks as well, so I think we'll save squaring this up for the next time, and that'll be the phase 2. This is a good point, good break point. Probably get a wedge under here and block this up, clamp down against the top of the vise to give this some support, because I have a feeling this would ring a little bit, and you know, that plate's a little thin. So I'll get some support on the tail end of this and simultaneously get it squared up, and then we'll start locating and boring that hole. So thank you for watching, thank you for subscribing. Till next time, as always, from Engineers Workshop, stay safe.